So what you're going to look today on the last section is series again, but what happens if you have an infinite series? Okay. What happens if you have an infinite series? So how do you add up an infinite amount of numbers? Interesting question, right? So back in 13.4, we go back there, and you just scroll back or flip your papers back. We had a formula that added up, like if you had 7 terms or whatnot, or 8 terms, all you had to do is take the first term and multiply it by 1 minus whatever the ratio is to that power, however many terms there are, right? And then you divide it by, what was it? 1 minus r. So that was the formula, and you could always plug in, 7 and find out, whatever that first term was. If it was 36, and if the r was, let's say, 1/2, it was going down by half, like each time, 36 to 18 to 9 to 4.5. Then you could just plug those in and find out, okay, those terms add up that many, add up to that much, right? And we could have done it manually; wouldn't take too long. But if we had to add up, let's say, 100 terms, we definitely need the formula. So the next question is, what if I have a series that does not stop? It has this dot, 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 meaning it's infinite. So anytime you see that dot, 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 it means it goes on forever. It's an infinite series. How do you add up an infinite amount of numbers? Have you ever added up infinity? Right? It's kind of an interesting question. Like, this is that borderline of calculus of where you're like, well, how do we go all the way with this and add up every number that comes after this? So, interesting question. So what we're going to do is take this formula, which I'll rewrite it, all right, and we're going to ask yourself, just like on your homework that everybody just finished 100%, of course, right? What happens if we take the limit of this as n goes to infinity? So pretend we're plugging in infinity. What happens to this formula? And this is where, again, we're transitioning to calculus thinking and critical thinking in math. It's going to change dramatically as you go from the pre-calculus stuff, which every class pre-calculus has been one of the steps, complete the square, don't forget the negative, this and that. And from calculus, it goes to, okay, we have basic formulas, but do you understand it? Does it make sense to you? Can you imagine, abstractly think, what happens if n's going infinitely big here? Okay. So very different type of the brain question. So ask yourself, and then r, of course, it has to be some number that's less than 1. That's important, because if we just plug infinity in here, and this is like 2 to the infinity, well, that's going to go to infinity, right? But you got to remember that with geometric series, r is something that's small, right? So if you take 1/2 to the infinity power, what happens to this number overall? Gets pretty much equal to 0, right? And 1 minus 0 is basically just 1. So we get this new formula that we can use for an infinite amount of numbers, and which is right here. Wrong thing. Yeah, this whole thing. Yep. And it's outlined down here somewhere. Yeah, I'll scroll down. So that's the same as this. All right. So that's what happens if we take the formula we already had and set the limit going to infinity. Basically, this 1 minus r to the end disappears, which makes the formula smaller. All right. So we can use this very basic formula to add up an infinite amount of numbers, as simple as it looks, which is kind of nice. They say in mathematics this is an elegant solution. That when you take something complicated and you do a little bit of work to it, and the answer becomes more simple to solve an actual more complicated problem. Right? Sometimes math does that. It's not always a big formula that you need to solve the more complicated things. Sometimes it's simple. Right? We just have to remember, and this is the hardest thing that for students is, when do you use this formula and when do you use this formula? That's always one of the more difficult concepts. After you learn, oh, you can sum this, you can do that, it's arithmetic, it's geometric, now you have all these formulas, just like you did on the quiz. Do you know when to use any given formula? Right? So if you're everywhere and you understand everything, make that your last question to answer. Do I know when to use all the different formulas? Because that will be the biggest task on the test. Okay? So that's what you're going to use, right? And we know they converge or diverge, and I'll give you the situations how you know when to use any given formula. Okay? So we know that, let's see here. If the numbers get smaller, right? If your R's are getting, I'll say here, try that again. If you notice the numbers in your series getting smaller, that usually means it converges, right? And it means your R is going to be, in this case it's 1/2, it's going to fall into this restriction to use the infinite series formula. So you can't just use this formula all the time on everything from now on because it's new. You have to ask yourself, number one, is it geometric? It has to be geometric. So you can see that means, like on your quiz, you had to check, are all of these R values the same? So from 12 to 6, it's 1/2. From 6 to 3, it's also 1/2. So you had to verify the R's are consistent for it to be geometric. Then you had to see if the R was actually less than 1, which means the numbers are getting smaller. If those two criteria are met, then it converges, and then you can use the formula. Otherwise, throw it out. No good. Like over here, we can see, yes, it's geometric because it's going up by 2, but this does not meet this criteria, right? The R is not less than 1 because these are getting larger, and if the numbers are getting larger, that means it's just going to go to infinity, which means it diverges. There's no way to do that. The numbers are just getting bigger and bigger and bigger, right? There's no way to add up an infinite number of bigger and bigger numbers. It's just infinity. All right, so little lingo, kind of wrap your head around that. Just two criteria, right? Is it geometric, and is the R less than 1? And they do say absolute value because technically it's okay if the R is negative 1/2, and we went from 12 to -6 to +3 to negative. That still converges. So it's okay to have a negative, right? Another way of looking at that is that it has to be between -1 and 1. The R's have to be between -1 and 1. And these two are this equivalent. Just like on your homework, for the limits, we said the absolute value of the function minus the limit has to be less than epsilon. That's the same thing as it has to be between the positive and negative of the two epsilons. So those are equivalent. We're not actually taking the absolute value of a number. This just means the same thing. It's the distance. So I'm going to practice just doing a few of these and go over a few details you probably have seen before, but maybe forgot the work here. So the first thing we're going to look at is partial sums, which just means add up the first number, the first two numbers, the first three numbers, the first four numbers. So this is more of a vocab problem. If you know what that means, the math is third grade math. Okay, so if you know what that means, it just means, okay, the first partial sum is 24. Whoa. The second partial sum is 24 plus 12. Ooh. All right. So nothing difficult about it. It's basic math. Okay, and don't have to overthink it. And then the third partial sum would be the first three numbers added up at the series, which would go to 6, of course. So that's going to be 36 plus 6, which is 42. And you can do the fourth one. What's the fourth partial sum? Continue the pattern. Add it up. See what you get. And it's nothing more than that. So of course you came up with the number 45. And in this sense it's kind of like a recursive function. If you just take the last answer and add up with the last term, 24 plus 12 is 36. 36 plus 6 gives you 42. 42 plus 3 is 45. So you could go re-add and say, okay, this one's 24 plus 12, okay, and the third one's 24 plus 12, plus 6, but you've already added up everything but the last term in the previous question. So, like a recursive type of thinking. And then, of course, it says, well, what happens if you add it up all the way? Right? So, we do know it's geometric, right? Because it's going down by a half each time. And we do know it's r is less than a half, right? So we establish it's geo, check. Establish r is less than 1, check. So you can use the new and approved infinite formula and see what the sum is. Normally this was s sub n because we were saying how many terms we're adding up. Technically we're doing s sub infinity. We're adding up an infinite amount of terms, but we don't really write the infinity sign. So you'll see on the formula it just has s equals, but it's really an infinite number of terms. So we have our first term, 24, minus 1 minus a half, which is 24 divided by a half, which equals, don't say 12. What does this equal? 48. Dividing by a fraction. So remember, division, it means, what kind of like, if you had like, I don't know, slices of pizza. If you have 24 slices of pizza, and you divide each of those slices in half, how many pieces do you have? Yeah, you divided 24 each of those in half, now you have 48 different pieces, dividing by a fraction. Okay. So you can go all this way and then sometimes just mess up on arithmetic and put 12. That's 24 divided by 2. That's 24 slices, and you have 2 people. How many does each get? 12, right? Lots of pizza. Yeah. So watch the details and you'll be okay. Now this is quite extraordinary. 48. Because if I continued this formula, let's say if I went from, and you don't need to write this down, but just need to understand it. Again, this is more about understanding. Let's keep going on here. So the next number after this would be what? 1 divided by 3, half? Be 1.5, right? And the next number after that, divide that by half, would be 0.75, right? And divide that by half, you get 0.375, right? These right here, actually I'll go, this would be, if I add up these numbers, this would add up to 6.5, right? And that's the first 1, 2, 3, 4, 5 terms. So the terms, A1 through A5 add up to 46.5. That means all the other terms from the 6th term to the infinite terms, to infinity, right? An infinite amount of numbers, the whole thing adds up to 48. Everything else only adds up to 1.5. An infinite number of fractions added up. Because 46.5 is just these. The whole thing equals 48 by the formula, so that must mean starting at 0.75 plus half of that, plus half of that, plus half of that, plus half of that, for an infinite number of times only adds up to 1.5. Right? Kind of interesting how you can add up. You think of adding up an infinite number of numbers, right? That's got to be huge when really, 1.5. That's it. And that's kind of things you kind of look at in calculus and figure out, well, how big, if you add up a continuous amount of fractions, how big is it possibly, right? Something that kind of bends your brain a little bit. Okay, so, question, yes?
So once it gets to 48, does it stop, or is the number so tiny that it doesn't even matter anymore?
Yeah, it gets infinitely small that you're still adding it, but it just never gets above 48. Yeah, it's infinite, so they're just too small to really make a difference in the full sum. Yeah. And it's cool how it comes out to like a 1.5. You think of adding an infinite amount of numbers, well, won't that come out to like, 2.37858, like some random decimal? It's like, no, 1.5. And we have to use a little thing, a little idea that 0.999 repeating, it actually equals 1. So if you have fractions that are 1/3 that equal 0.3 repeating, 1/9 that have 0.1 repeating. Well, those actually equal whole numbers if you do the math on them. And this isn't not it doesn't I'm not saying it's about like close to, but mathematically these are the same number. 0.9 repeating forever is the exact same thing as 1. Where you're like, wait a minute. No, 1 is 1. That's never going to be 1. But if it's going to 0.9 repeating forever, you know, like, yeah, and there's ways of proving it, and we'll get to that a little later. But this is one little reason why this comes out to a nice number, is that these repeating decimals actually can add up to nice full integers. Okay. All right. So there's one little over here, a little sigma series by itself. So what does this add up to? So if you're given the sigma, you just have to write out the series and figure it out. So plug in 1, the first term would be 4 times 1. Okay. Plug in 2, the second term would be 4 times 2, and so on. So what does this infinite series add up to? Because it's going to infinity as well. What does this add up to? All right, give that a think, talk about each other, decide on which you agree the answer is real fast. All right. Does anybody want to render a possible solution here? Yes? Anybody? In other words, what? It diverges because mathematically. Yep, and right here. So made a very clear point at the very beginning. It's geometric, yes. Is r less than 1? No, r equals 2. Therefore, we cannot use this, right? So it's more important to know when to use each formula. That's how I started with, than the formula itself. The formula itself is basic arithmetic from the 4th grade. That's when you learn to divide fractions, right? So don't worry about the formula and getting a number. That's old school thinking. You're more concerned about what you're doing and why you're doing it. That way you don't just start using formulas all the time everywhere when you shouldn't be using it. So it's more important when to use the tool than using the tool itself, right? So it's like looking at trying to fix something and you have all these tools, screwdrivers and wrenches and drills. It's more important to know what tool to pick up than just grabbing any tool and just starting to use it. You know, if you got a screw you're trying to unscrew, you can't pick up a hammer. That's the analogy that kind of works the best. You got to know when to use which tool. Way more important than actually using the tool. Yeah. Yep.
So for that answer itself, if we were to go on, of course we get infinity. But is the infinity bigger than the infinity on top, or are they both like the same thing?
Say again, infinity what?
If we have the infinity that we have right there, right, and we do 4 and the 8 and the 12 because we're multiplying by 2 each time.
Yep.
Since we're having less numbers inside of that infinity, wouldn't that infinity be bigger than the infinity on top of the sigma? Because that infinity goes by 1.
On top of the sigma?
Because that infinity on the top goes by 1, right? 1, 2, 3, 4. But the infinity that we're getting as our answer is an expression of multiplied by 2 from the last term. And then you said the infinity has more numbers in it. It's bigger than the last infinity, no?
If this series has bigger numbers, then yeah, this infinity will be bigger than just doing 1 plus 2 plus 3. Yeah.
Okay.
I see what you're saying. It doesn't really affect the answer here, but yeah, that's true. Yeah. Yeah, that's a point from last week, if you remember, that infinities are not all equal to each other. So 1 plus 2 plus 3 plus 4, and you do that forever, it equals infinity. And this one, 4 plus 8 plus 12 plus so on, also equals infinity. These two infinities don't equal each other. This infinity on the bottom is bigger than this infinity. Kind of messes with your head. Like, how? It's infinity. It's the biggest number. No, like some infinities are bigger than other infinities. That's what he's getting at, right? So, and that's a question. Once you get into actual calculus next year, you start figuring out how to answer this question a lot more definitively, and you have more strategies, you have more formulas, you have different things we can do involving derivatives. Same thing if you are taking limits, right? And you get 0 over 0. There's some tricks that we can do with this, and like we divided everything by the highest power or the highest degree, right? And that could help us solve it. Well, there's more tools like that. So this is just a preview of looking at all this infinite funness. Okay. Yep.
Did you say that the signal was geometric?
Yes, we're assuming that, yeah, this is geometric, yes.
How would you get, like, how would it be geometric if you're going from 8 to 12?
How is it?
Yeah.
Plug in 1, plug in 2. Oh, that's true. Also not geometric, right? Yeah. Good way to prove it, too. So, going back to how do you actually prove something is geometric, he's saying that the r's have to be equal. Then we look at this, and we say, well, 8 over 4 equals 2. And technically 12 over 8 doesn't equal 2, does it? So that would equal 4 divided by 4. That would equal 3 over 2. So that's actually 3 over 2. So another reason why we should not use the formula is that the r's are not consistent. This is 3 over 2. Good point. Very good point. Yeah, so you guys got some good rest over the break, I can tell. Brains are firing on all cylinders. Excellent day. Okay. Why don't you guys try this one? Why don't you go try A? Okay. Definitely check both criteria, and if so, add them all up. Infinite amount of numbers. Try that out. So we established that the R is definitely consistent. So it is geometric. Right? So I did the second term over the first term, 24 over 36, got 2/3. I did the third term over the second term, 16 over 24 is also 2/3. And then we verified that that is indeed less than 1. Therefore, you can go to the formula. So always want to check that criteria just to make sure. So you're going to take that first term and just do 1 minus the R. Which at this point, it means it definitely converges. Even before you get the number, you know that there is some number because the formula does indeed work. So we got 1 minus 2/3. And 36 over 1/3 equals 108. Yeah. 108. And that's 1/3 right there. 1 minus 2/3 is 1/3. And just for giggles here, I'm always interested in looking at this. So if I continue this pattern and keep on doing 2/3 and 2/3, this will be plus like 10.6 plus 7.1. I'm just doing 2/3 over and over and over. And I always like to take this all the way to the point where it becomes less than 1 and see how much that adds up to. 1.4, right? And then it goes to 0.9, something less than 1. And then it keeps on going forever from there too. So all of these numbers, I already kind of did this for you, all those add up to 107-ish. Like basically 107. So the first 1, 2, 3, 4, 5, 6, 7, 8, 9, right? First 9 terms add up to 107. That means and the whole thing adds up to 108. So that means starting here, going to an infinite high number, those fractions all add up to 1 to get you to 108. If we have 107, one more gets you 108. So it tells us how much this huge part of this, main part of this series that goes on for infinity only adds up to 1. All those fractions nonstop added up equal 1. Kind of interesting. So that's why we focus on 1 over n so much. Well, 1 over 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7, that actually only adds up to uno, just 1. So something interesting. We always expect to add, when you're adding of an infinite amount of numbers, it should be some big answer, right? And the fact that it comes out to exactly 1, not close to 1, not kind of 1, but exactly 1 is even more interesting. All right, so the last one is just a different type of problem. It's the same problem as A, just rewritten a little bit differently. So there's a way to figure out the same thing, but for repeating fractions. So if we just acknowledge real fast that 0.45 repeating is 0.45, I'm going to do this in different colors. 45, 45, and just keeps on going on forever, right? Well, you recall back in, I don't know, probably 3rd or 4th grade, you did something called place value. So if you had 343, I'll do 342. You can rewrite that as 300 plus 40 plus 2, right? Because this is the hundreds place, so this is equal to 300. This is the 10 place, so it's equal to 4 tens. And this is the 1 place, so it's equal to 2 ones. We can do the same thing here, just with decimals. Right? So, of course, 0.45 is equal to 0.45. But this right here, tenths, hundredths, thousandths, 10,000ths, is equal to 0.0045. Right? And, of course, this 45, the red one, is going to be equal to 0.000045. And then that will keep on going on forever, plus ... So now it's kind of written like one of these infinite series up here. And it also is geometric, because the ratio is the same. This is just dividing by, or multiplying by 1/100th each time. So we can use this formula, just like before, to find out what this is as a fraction. So that's the ending, on the end it's going to give us that answer as a fraction. So all we have to do is throw it in there. 0.45 is the first term. And then we know the R value is 1/100th. Simplify that, and that'll tell us what this equals as a fraction. One of many useful uses for this. And if you kind of do any coding and calculations, you know that you can get stuck in infinite loops if you're dealing with infinite numbers, and these are some tricks to get around that. So what is 1 minus 100? 99 over 100, right? Because 1 is the same as 100 divided by 100. So 100 minus 1 is 99. Then you can solve this. Divided by a fraction, multiply top and bottom by the reciprocal. And it's amazing how much of, arithmetic you have to be really fluent at, to make sure you get these correct. Again, more 4th, 5th grade math. Just dividing fractions was from, elementary school. I just want to make sure we do that very carefully. And we have, 0.45 times 100, right? That just moves the decimal twice, so you get 45. And then denominator here is 99. And the nice thing about this is that you could always take a calculator and just punch in what's 45 divided by 99, and you'd get 0.45454545 and so on. If you don't already know this, often when you divide by 99s, 9s and 6s and 3s, that's when you get the 0.3 repeating, the 0.6 repeating, the 0.9 repeating. So a lot of repeating decimals come from denominators with 3, 6, and 9s. Not always, but that's the fastest way to get a repeating decimal. Okay. So, in other words, 45 divided by 100 equals just 0.45. You drop the denominator down by 1, it turns into 0.45 repeating. So if you have a decimal and you want to know, well, how do I make that into a repeating decimal? Usually you drop the denominator by 1 and it becomes repeating. Fun fact. Okay, hours of entertainment right there. Okay. Especially for rainy days. Okay, so that's it for today. Again, pretty simple, more of a conceptual, more of understanding when you use a formula. Not so much the formula itself is super basic, right? We made a big right turn from, like I mentioned before, hyperbolas and parabolas and completing the squares and number-based questions to conceptual thinking, all these different types of infinity, how do you add up an infinite amount of numbers, right? Different type of the brain stuff. Very cool. Okay, so let me post the assignment and let you guys get to work.